We can start with our warm-up problem, which is a really good reminder of what we talked about last time. So we're given that g of xy is 4 minus 6x plus 8y minus 2x squared plus 5xy plus y squared is the second order Taylor polynomial for this function f of xy at the point 1, 1. Now, we do not know what f is. We know that g is the second order Taylor polynomial for f, but we don't know what f is. Now the question, which of the following is the tangent plane to f of xy at the point 1, 1? And we have 5 options here. Does anybody know which one it is? A. A? Oh, bold choice. You're looking and saying, hey, Steve, I have eyes to see. You can't fool me, but I'll point something out, which might make you say, Now, I'm not saying A is not right. Notice there's this point 1, 1. Now, if it's at the point 1, 1, what should our pieces look like? In terms of, it shouldn't look like x's and y's. What should it look like? It should look like x minus 1s, and it should look like y minus 1s. So what happened? The fools, they expanded. They shouldn't have done it, but they did. So it's not necessarily that, but it's really tempting. Really tempting. Now, could be right, could be wrong. But now that I've said that and made you doubt, anyone else have an answer? Or are you confident about A?
C.
C?
C.
C? Anyone else?
C.
What?
C.
C? Anyone else? Okay. Well, the answer is E. Okay. So, let's talk about it. Okay, so now how do we actually solve this problem? Well, we can't just read it off. That was very tempting. I can tell you that you can narrow it down to B or E very quickly. And I'll point that out in a second. But before we do that, we should understand what a Taylor polynomial is doing. Because if you understand what a Taylor polynomial is doing, you understand what this problem is asking. And you'll understand how to use Taylor polynomials in the future. For example, maybe on a test. So we say, well, it's like the best polynomial. But here's how I like to think of it. The Taylor polynomial, it's storing derivatives. So if I have the Taylor polynomial, it's storing the derivatives of the function. So think back, even in Calc 1, we said, hey, a tangent line says what? Well, if I know the value of the function and the value of the derivative, I have the tangent line, but also vice versa. If I have the tangent line, I can tell you what the derivative is. I can tell you what the value of the function is. So what's happening is that we form the Taylor polynomials by saying, oh, let's put in all our derivatives. But now we can also extract derivatives from it. In particular, this is matching all the derivatives of f, well, not all of them, all the derivatives of f up to what? Second order derivatives. And how do we know it matches up to the second order derivatives? Because it says it. All right, so we say, aha, really what that says is if I know what the tangent plane to G is, because what information do I need to make a tangent plane? Value of the function. What else to make a tangent plane? I'll give you a hint, there's 3 things, so there's 2 more to go. Value of the function. Well, the normal vector, okay, right, but where does that come from? Gradient. What's inside the gradient? We're almost there. Partial derivatives, and there's 2 of them. So you need f sub x and f sub y. So the tangent plane stores three pieces of information: the value of the function and two partial derivatives. G is storing actually even more than that. So we just have to say, well, we'll just pull out of G what we need. So for instance, we can say the following. F at 1, 1, it matches what G does at 1, 1. So plug in 1 and 1 into this. What do we get? We get 4 minus 6 plus 8 minus 2 plus 5 plus 1. And, well, here you have this minus 6 plus 8 minus 2. So that's going to go away when we get 10 out. So we know the value of the function at 1, 1 is 10. Now, here's a quick thing we can do. That says the tangent plane at 1, 1 should be 10. So plug 1, 1 in. Into A, what comes out? If you plug in x equals 1, y equals 1. 6. That's not 10, so it can't be A. When you plug 1, 1 into B, what comes out? 10. Could be B. How about into C? Not 10. It's 3. How about D? 5. Not 10. How about Z? Sorry, E? 10. So we already know with just this one piece of information, it has to be B or E. All right. So now I've at least convinced you it's not C. I haven't convinced you yet it's E. Now, how do we get our partial derivatives? Well, we say, let's figure out what G sub x is. We can do that in general. G sub x of x comma y. That's negative 6 minus 4x plus 5y. So then the f sub x at 1, 1 has to match G sub x at 1, 1. Because G is storing partial derivatives. So they have to match. And now we plug it in. Minus 6 minus 4 plus 5. So that gives us a negative 5. So which one of these two has f sub x equal to negative 5? Well, it's definitely not B. So we now know the answer is E, but we'll keep going. All right. And, well, similar process, G sub y of x comma y. So take derivative with respect to y. We get 8 plus 5x plus 2y. Plug in 1, 1. 8 plus 5 plus 2 makes 15. And in case you're still not convinced, we'll just remind ourselves the formula for the tangent plane, f of AB plus fx AB times x minus a plus f sub y AB times y minus b. And so we put these numbers in. We get 10 plus negative 5 times x minus 1 plus 15 times y minus 1. And if you expand, you'll see you have a 10 plus a 5 minus a 15. The constants go away, and you get minus 5x plus 15y. So there we go. But the key here is just to understand, hey, Taylor polynomial is storing derivatives, and be careful. Sometimes they do foolish things like expand. But that's okay. Even if they expand, the derivatives are still being stored. We just have to extract them by figuring out, okay, let me just take the derivative I want and evaluate to get what I need. All right. Well, any questions on that one? Good times, good times. All right. Well, on to today. Thought for the day from John Ronald Reuel, Tolkien. Shortcuts make long delays. Well, he wrote fantasy, and one of the great fantasy writers, people would argue. And but this is true in life. A lot of people would say, look, I'd really like to say, what's the short and easy way out of math? And if you've ever thought that to yourself, don't worry, you're not alone. This goes back thousands of years. Even at the very first time when they had math tutors, the students would ask, isn't there an easy way to learn math? And the tutors would say, no. The quote in particular, there was a prince studying math, trying to learn geometry. And he said, come on, give me the easy way to know this. And he said, no, there's no royal road to geometry. You have to take the path. Now, what am I trying to say? If you want to learn math, you have to go through the crucible. You got to put in the time, the effort, and the energy. It'll come at some point sooner or later. Don't have to repeat the classes. We don't want you to. I mean, maybe Iowa State wants you to because it helps their budget, but I don't want you to. I want you to go on and succeed. So invest the time now. Make the journey short. Go the route, so to speak. Now, our goal for today, we're starting optimization. There's 3 lectures on optimization. Each lecture has a slightly different theme, but we're building up. So this is the first lecture on optimization. And we're going to talk about critical points. This might sound familiar. You think back to Calculus 1. And you said, I learned about critical points. That's where the max and mins were. So that's where we were interested. We wanted to find those. Those were in the important points. And if you think back to what that was, we'd say, well, it's where the derivative is 0, or the derivative is undefined, or the endpoint. And now we say, well, instead of the derivative, we put the gradient. It's where the gradient is 0, the gradient is undefined, or the boundary. That boundary is acting like the endpoint. So it's very similar, highly similar. Now the next thing is like, well, we found a critical point, but what is it? Is it a max? Is it a min? Is it something else? So that gets into classifying, our classification. So we need a way to test. And so that's what we're going to do. It's called the second partials test. And there's a procedure. You compute a number, and then you interpret that number. Now, that looks like a lot to learn for the second partials test. So I'll point out it's written on the formula sheet. So the second partials test is there. It's one of the 3 formulas from this part of the course that's on the formula sheet. But we still have to understand what it is and how it works. So we'll get to where this number comes from and get to why it tells us whether something is a minimum, a maximum, a saddle, or there's no conclusion for us to make. So that's where we're going for today. All right, so we'll start with a few basic ideas. This will look very similar. We're talking about optimization. That's where we're looking for the est, the biggest, the smallest, the tallest, the shortest. If you can make a word that ends with est, you're doing optimization. You're trying to get the most out of the resources you can. And there's an idea of maximums and minimums, and also the idea of absolute or global versus local. So these should be sort of intuitive. You're an absolute max, in other words, you're as large as possible if every other point, when you plug into the function, produces a smaller value, or a value that's less than or equal to what you are. So that's for all points, regardless of what you're doing. You're a local maximum if everything that you plug in is smaller than we're at, but when you restrict, I only need to see what's happening near the point I plug in. So absolute max, you look over all possible inputs. Local max just says very nearby, very close. But it's the same processes as before. We're going to come and use the idea of the gradient. We've talked about properties of the gradient. One of the key things it does is it points in the direction of greatest increase. If you go negative the gradient, that points in the direction of greatest decrease. So, what's true? If I'm at a point and there's a gradient that's not 0, and I want to get bigger, what should I do? I should follow the gradient. The gradient says you should go this way, so I go this way. And what's going to happen? I move up. If I'm at a point and I want to get smaller, what should I do? Go opposite the gradient. And I go down. Now, I'm not going to have to move very far, but that's okay. All I need to say is, if the gradient isn't 0, and I have the ability to move, I can go up and I can go down. So I am not at a max or min. So that rules out very quickly a lot of points. And so it says, okay, where do we put our focus? Well, what needed to happen? We needed to have a gradient, and we needed to make sure it wasn't 0, and we had to have freedom to move. So where do we look for our maxes or mins? Well, look for where the gradient is 0, where the gradient is undefined, or the boundary. Now, I'll be honest with you. I will tell you, gradient equals 0. This will be today/tomorrow. Well, I shouldn't say tomorrow. Today/next time. The boundary, we're going to talk about that next time. Where the gradient is undefined, don't worry. We're going to work with nice functions, so we're not going to worry about that. So we're going to focus today where the gradient is 0. That's our goal. That's our goal. So when we talk about critical points, really we're saying, hey, let's figure out where the gradient is 0. Any questions on that? All right, let's try this out. Find the critical points for the function f of xy equals 2x cubed minus 2x squared y plus 6xy plus y squared minus x squared. Okay, so we see critical points. We also see this as a nice function. We're not going to worry about gradient being undefined. Is there any boundary involved in this problem? No. That's next time. But for now, there's no boundary. So when we see a question phrased this way, with this type of function, what is it we're looking for? Yeah. So we can rephrase this as the following. So rephrase as find where gradient of f equals 0. Which becomes partial f partial x equals 0 and partial f partial y equals 0. Because when we talk about the gradient equals 0, we really mean the 0 vector. The art history major of vectors. All the entries are 0. It's zeros across the board. So we get 2 equations. We love 2 equations. All right, so partial f partial x equals 0, so we're going to take our derivative with respect to x. When we take our derivative with respect to x, what do we get?
6x squared.
6x squared.
Minus 4xy.
Minus 4xy. Plus 6y. Minus 2x equals 0. Partial f partial y equals 0. Derivative with respect to y. Minus 2x squared plus 6x plus 2y equals 0. All right, well, good times. Woohoo! Now, what do we get? Well, we're going to get 2 equations and 2 unknowns. But now, this is not our bread and butter, 2 equations, 2 unknowns. You have to work a little bit harder most of the time. So what tools do we have? Well, let's talk about a tool you almost never get. You almost never get elimination. It's one of my favorite ways of doing 2 equations, 2 unknowns, but that's when we have nice equations which have linear terms. You see things like squareds and xy's. So the 2 main things to look for, substitution is one, and factoring is the other. So be ready to pull those out. Does anything obviously factor here? Or maybe slightly less than obviously factor?
2.
Okay. We can divide everything by 2. Woohoo! Nice. Okay, we'll rewrite that. X squared minus 2xy plus 3y minus x equals 0. And minus x squared plus 3x plus y equals 0. Did I get that right?
3x squared in the first term.
Ah, thank you. Thank you. All right. Well, that was fun. I don't see a really good factoring here. Maybe we'll see one later on. So, that's okay. We have more than one approach. I mean, we have factoring. And if that doesn't work, we can try substitution. And if that doesn't work, we can say, have you heard about factoring? So, and if that doesn't work, we should say, maybe we should take our partial derivatives. All right. Is there a nice substitution? Now, when we talk about substitution, that means we want to take one of these equations and solve for one of the variables. Is there one variable we can solve for fairly easily? Well, the reason I'm asking you, you meant the variable y. Oh, I'm so sorry. Oh my gosh. Okay, yes. We can solve for y. Y is x squared minus 3x. So what are we going to do? We're going to take this and put that into our first equation. So we get 3x squared minus 2x times x squared minus 3x plus 3 times x squared minus 3x minus x equals 0. Now, what's happening? Well, what's happening is we're going from 2 equations with 2 unknowns to 1 equation and 1 unknown. In theory, easier problem. It's a great theory. All right, well, what comes next? Yep, we're going to multiply things out, being careful with our signs. So we're going to get 3x squared minus 2x cubed plus 6x squared plus 3x squared minus 9x minus x equals 0. Well, we group. For the x cubes, we just have the single minus 2x cubed. For the x squareds, we've got a 3x squared, a 6x squared, and a 3x squared. If we put those together, that gives us 12x squared. And then for the x's, we've got a minus 9x and a minus x, which makes a minus 10x. All right, so we just have to factor a cubic and we're done. Oh, we can pull out negative 2x. So that leaves us with x squared. What's the next term? Minus 6x plus 5 equals 0. So that makes it a little bit easier. We already have made progress. Now we just have to factor that quadratic. Does x squared minus 6x plus 5 factor? He says, writing it down like it does. X minus 5, x minus 1. So, what are our answers for x? 0, 5, 1. Right? One of these three has to be 0. That's the power of equals 0. So if it's the x term, that's where you get your x equals 0. If it's the x minus 5 term, that's where you get the x equals 5. And if it's the x minus 1 term, that's where you get the x equals 1. Now, we need points, not x values. What are we missing? Well, I'm asked. Oh, no. I won't do it to you twice in a day. Well, I will, but okay. We need to get the y, and that goes back to our substitution. If x equals 0, what is y? Yeah, 0 minus 0. If x equals 5, what is y? 10. If x equals 1, what is y? Negative 2. So these are our critical points. 0, 0, 5, 10, 1, negative 2. All right. Any questions? In that case, there's another problem. More aimed at closer to the level of what we might put on an exam for right now. Find the critical points of, and here's this function, 3x cubed plus y squared minus 9x plus 4y. At the very least, it's a lot shorter to say. How many points did we find? 2. What are the points? 1, negative 2. Negative 1, negative 2. All right. Yes? Yes. All right. So really quickly, what's the idea? G sub x. 9x squared minus 9 equals 0. Well, that just becomes, divided by 9, this is the same as x squared equals 1, which is the same as x equals plus minus 1. G sub y, 2y plus 4 equals 0. Now, move the 4 across, divide by 2. Y is negative 2, which is the same as y is negative 2. And when we're talking about solutions, we have to say, we need both equations to be satisfied simultaneously. So, what are a pair of points? Well, I always have to have negative 2 to make sure the second equation is satisfied for y. And then for x, I have 2 options, 1 or negative 1. So that leads to 2 points. Don't worry, we'll get to do more with this problem in a little bit. Because we found the critical points, but the story doesn't stop there. Now we want to classify. So let's do a little bit of a discussion. Classifying critical points. So don't worry, most of this is recall. So if you think back to Calc 1, we had 2 tests. The first derivative test, which says, let's look on what's happening on either side. And then I can say, I'm coming up on one side, I'm going down on the other side. Like, I know what I am. And we're like, first derivative test. We loved it. It was such an easy test. It was our favorite test. We can't use it in multivariable calculus. What's the issue? Well, in single variable calculus, you only have to check 2 sides. Because when you think about a critical point, it's like, what's on the left? What's on the right? And that's only 2 sides. When you go into multivariable, how many ways can you approach a point? Well, sure, you can go along an x, or you can go along y. But you can approach in many different directions. There are infinitely many directions you can approach. You can check 100 directions, and every one of them can tell you, this is looking like a maximum, but there's a direction that says, actually, it's not. So you cannot conclusively say, hey, I've checked a bunch, it must be. So that's out. And I said, well, that's okay, because they made us learn a second test. We called it the second derivative test. And the second derivative test says, look at what's happening to f double prime. If f double prime is positive, we're at a minimum. If f double prime is maximum, sorry, if f double prime is negative, we're at a maximum. And if f double prime is 0, there's no conclusion to be made. The way I remember that is I say, well, if the second derivative is positive, our curve is bending like this, so we look like a minimum. If our second derivative is negative, our curve is bending like that, so we look like a maximum. And if our second derivative is 0, we don't know what's going on. Now, why does the second derivative test work? In Calc 1, we said, oh, it's about concavity. It's about how the curve is bending. And that's true. But that was our Calc 1 understanding. If we put on our Calc 2 hats, we say, well, you know, let's think of this as a polynomial. We can approximate what's happening to our function by the value of the function. We're at a critical point, so f prime of a goes away. And then there's the next term in the Taylor polynomial, this f double prime of a over 2 times x minus a squared. In particular, this part is driving behavior. If this second derivative is positive, you have a positive coefficient in front of a square term, you open up. If this second derivative is negative, you have a negative coefficient in front of your square term, so you open down. And if it's 0, it says, oops, you don't have enough information, you have to go deeper into your Taylor polynomial. So I say, so it's the second derivative, and what's happening with that, that drives the behavior. Now, that's context. Here's the test. We're at a critical point. We think back to last time, because we talked about Taylor polynomials. And last time we said, if we're at a critical point where the first derivatives are 0, our function looks like the value of the function plus 1/2, and there's this sort of delta x, delta y pieces. And then there's this 2 by 2 matrix. That's acting like our f double prime. So, what goes on? Well, when you take a class called linear algebra, great class, highly recommend it. It turns out when you have 2 by 2 matrices, you get two special numbers called eigenvalues. If your two eigenvalues are positive, it's the same as if f double prime was positive. It says you go up in all directions. So you look like a minimum. If both your eigenvalues are negative, you go down in all directions, you look like a maximum. But there's another interesting case which says, oh, in some direction you go up, in a different direction you go down. That says you look like a saddle. So you're not a max or a min. It's this ambiguity. Well, all right, that's great, but how do we figure this out? Well, the key is to say we need to know the signs. What's going on with lambda 1, lambda 2? And there's this fun fact that if I want to compute the product, you can do what's called the determinant. If you're familiar with 2 by 2 matrices, that says you multiply down one diagonal, subtract multiplying on the other one. So this is the determinant of your matrix, fxx, fyy, and fxy squared. You find this number. It's a number, because you're at a point. If that number is negative, that says you have to have opposite signs. You're at a saddle. If that number is positive, you're one of these two things. You're either a min or a max. So you have to say, but which one? And here's the answer. Look in a slice. So, if we slice, we can say, let's look at it as though we're looking at it just as a function of x. So I can go back to the second derivative test from Calc 1. So if fxx is negative, we're at a max. If xxx is positive, we're at a min. By the way, there's nothing special about fxx. You could use fyy. But essentially what you're saying is, I know it's a max or a min. Let me look in a slice, and let me go back to an earlier second derivative test. The last thing is, if you get 0, that means at least one of your eigenvalues is 0. You do not have enough information to say what the shape of the surface is doing. So you can't say max or min. Inconclusive. All right, so that's the test. As a reminder, this is on the formula sheet. So don't stress about memorizing it. Stress a little bit about using it. Are there any questions before we try this out? All right. Well, here's a problem. A little bit of deja vu. Let's classify the critical points. All right, so we already know what the critical points are. We have them listed here. If we're looking to classify, what do we need to be computing? The second derivatives, which now I like, well, let's move this down a little bit. We have the first derivatives, right? So that we have our f sub x and our f sub y. We need all of them. So we'll look at fxx, and I'll just write these down in the interest of time. 12x minus 4y minus 2. Fyy minus, 2. And fxy. That's take derivative of f sub x with respect to y minus 4x plus 6. Yes. Yes. All right. By the way, at this stage, I claim there are no maximums to this surface. Can you see why? Fyy is always positive. If Fyy is always positive, you can't have a maximum, because you need Fyy needs to be negative at a maximum. All right. Well, pick a point, any point. How about 0, 0? That sounds like a good point. Okay, so recall D is fxx times fyy minus fxy quantity squared. So D at 0, 0. When we plug 0, 0 into fxx, what do we get? Negative 2. When we plug it into fyy? 2. When we plug it into fxy? 6. Now, you don't have to worry about the value. The value is not important. What do we want? The sign. Can you tell me what the sign is? It's negative. We saw the sign, and it opens up our eyes. What does that tell us about 0, 0? If where are we? I have to go back to this page. If we're negative, what are we? Saddle. All right, we are a saddle. Okay, one down. Let's go to the next one. So we'll do 5, 10. Okay, so 12 times 5, 60, minus 4 times 10, minus 40, minus 2, times 2, subtract, minus, it's minus 20 plus 6. Yes? 60 subtract 40 subtract 2. Anybody know that off the top of their head? Yeah, so this is 18 times 2, which is 36. And I forgot to square this. We're going to subtract 14 squared. We don't actually need to know the number. The question is 14 squared bigger than 32? Yeah. So what's the sign? Negative. So what's 510? Saddle. Spoiler alert, you will get lots of saddles. Just to be honest with you, with the functions we deal with, expect many saddles. Many saddles in 1 point, that's not a saddle. Maybe if you're lucky, I think I've been able to get one time when I got like a min and a max and 2 saddles, and I was really proud of that one. That got on the exam. I was super proud of that one. Okay, so here we go. 12 times 1 is 12 minus 4 times 2 plus 8 minus 2 times 2 minus 4 plus 6 squared. 12 plus 8 is 20 minus 2 is 18 times 2 makes, whoops, why did I put 32 here? I know how numbers work. It's 36. Don't worry, 36 minus 14 squared is still negative. So it's 36, subtract 2 squared. Positive. Okay, so it's not a saddle. Now, what is it? It's a bowl. But is it a bowl going up or a bowl going down? What do we look at? We look at either x, xx, or y, fyy. Now, the good news is we have those numbers. This is fxx. This is fyy. What do you see about these numbers? They're both positive. They have to be the same sign if you're at a local max or a local min. Both positive. Therefore, this last point, whoop, I lost place. Here we go. This last point is a min. All right, I know we're almost out of time, but can we classify these really quickly? What is gxx? 18x. What is gyy? 2. What is gxy? 0. So D is 18x times 2 subtract 0 squared, which is 36x. D at 1, negative 2 is what? 36, which is positive. Aha! So what does that tell you? It's a max or a min. So now the question is, which one is it? gyy is positive, so we are min. D of negative 1, negative 2. Negative 36. Negative saddle. And that's the process. All right.